Okay, today I will talk about resource allocation in wireless networks under uncertainties. I presented similar slides in the wireless symposium as a tutorial, so I will focus only on the first third of this talk, so I will not go that deep into formulating specific problems because there are many wireless resource allocation problems in wireless networks that we have studied in our group. So the focus will be in presenting the framework, why we need to consider stochastic optimization in resource allocation in emerging wireless networks, and what do we mean by stochastic optimization, what are the different approaches, etc. Yeah, so I will start with the motivation side and then give an overview about stochastic programming. And then we'll mention some of the example resource allocation problems that we have studied without going into like lots of details about these specific problems. And then the conclusions. As all of you, I think, know, optimization problems and their solutions are central to the design of protocols, algorithms, and resource allocation in communication systems and networks. And there are many examples for that: channel assignment, routing, shortest path routing, optimal receivers, etc. In wired networks, we know that the resources are plentiful, dedicated, controllable, and you have some, to certain level, deterministic knowledge about the quality of the resources that you have and how much these resources can provide you. The demands are, even in wired networks, are still stochastic, but the point is that although the demands are stochastic, the resources are plentiful, and you have some deterministic knowledge about the quality of these resources. In wireless networks, this is not the case. You are talking about more limited capacity. The resources are more scarce and limited. Also, the quality of these resources, whether you're talking about rates that the channel can support or other types of resources, they are usually stochastic, and you don't have deterministic guarantees on the quality of the resources that you have in a wireless network. In addition, for the demands being also stochastic. So for example, the wireless channel gains are stochastic, and this might be due to several reasons: the mobility of nodes, the mobility of the environment, the uncertainty about the propagation environment, etc. This happens in wireless networks and wireless communications in general on all frequencies, especially if you're talking about millimeter wave. We're talking about very highly dynamic network. And other special also type of network that you have lots of dynamic sources is in dynamic spectrum access systems. As an example, if you're talking about LTE Wi-Fi coexistence, if you want to do resource allocation for the LTE network and you don't have deterministic information about the Wi-Fi activity over different channels and how much data rate different channels can support given the different Wi-Fi activities on different channels, how could you design or you do resource allocation for the LTE network while still providing some QoS guarantees to the LTE users? So the scarcity of the wireless resources and the uncertainty in their quality and the demands of the users make it difficult to have guaranteed quality of service, deterministic quality of service metric, whether coverage or capacity. So in this case, we will talk about some probabilistic guarantees, how you can provide this quality of service metrics, whether coverage, capacity, in a probabilistic sense. This is one thing. And the other thing also, you want to be able to respond dynamically to the variations that happens in the network, the variations in the availability of the resources, the variations in the demands or the quality of various resources, etc. All of these things cannot be done in typical deterministic optimization. Also, in some cases, you might be able to do deterministic optimization, but stochastic optimization can reduce the cost that you will incur significantly. So in some type of networks, even if you are talking about like the resources being deterministic, you can design, if you do the optimization in a stochastic way, you can save the amount of resources that you need significantly without degrading the performance that much. Instead of talking about always satisfying all the users all the time, if you talk about probabilistic QoS metrics with talking about 99% of the time, etc., not much reduction, but you will see a huge saving in the resources. Some important applications that has the dynamics and the uncertainty are clearer than other applications when we're talking about millimeter wave, for example, networks. So the links, the availability of the links are very highly dynamic. Even without talking about mobility, even just changing the orientation of the user might make the link is no longer valid. Just a small change in the orientation of the user equipment might make the link with the given millimeter wave access point is no longer available. So the links are very highly dynamic in millimeter wave. We talked about LTE Wi-Fi coexistence, and there are many other applications in 5G where you have many sources of dynamics and uncertainty in the networks. That's why we propose using stochastic optimization as a framework for performing resource allocation instead of the deterministic optimization. So I will talk briefly about, or giving an overview about stochastic optimization in terms of what type of models for uncertainty we could have, and what are the different approaches that we can follow to optimize the resource allocation problems under uncertainty, and what are the different ways to define the feasibility region of the optimization problem under the uncertainty of different variables. Modeling of uncertainty. The first one is there is no uncertainty, it's just deterministic. Or actually there is uncertainty, but this is the common approach that has been used in wireless communication and networking research, is just whatever stochastic variables you have, fix it on the expected value. And this is not always good, because the actual realization of this variable can have a value that is much higher than the expected value or much lower. So this is not efficient in terms of the resources and in terms of even of user satisfaction to just fix whatever stochastic variable in its expected value. The other type of modeling is to use range modeling. So you say this variable can take a value from A to B and optimize considering this range of values that a given parameter or variable can take. The third approach is to know the full probability distribution that a given stochastic variable has. So you know that this is stochastic and you know its probability distribution. And the last, and this is the most commonly used approach in stochastic programming. The last one is to know, knowing that the variable is following a set of distributions, but you don't know exactly which distribution, or you know the distribution, but you don't know the exact parameters of the distribution. So it's not as the third bullet when we know the full probability distribution. So what do we mean by stochastic optimization? This is typical deterministic optimization problem. You have an objective function and you have equality and inequality constraints. The stochastic optimization, if the objective function or these constraints, gi of x or hi of x, have some stochastic variables. So in deterministic optimization, you have data that is deterministically known, and then you have your decision variables that you want to decide about optimally. And everything else other than the decision variables are known to you. What if you want to optimize something, but under the uncertainty of some of these data? So the data is it's not deterministically known, it's just stochastic. There are different approaches for optimality, and I mean by approach to optimality is how to define the objective function under the uncertainty. So one way is to take the expected value, the expected cost, the expected value of the objective function. Another way is to take a function of the mean and the variance, or the mean and the standard deviation. And in this case, you consider the deviations of the mean in both directions. And you have this parameter that you take the mean plus some constant times the variance or the standard deviation. And this is basically the degree of risk that you have, or the risk that you can afford. The third approach is to formulate the objective function as a probability. So you have, let's say, f is function representing the user unsatisfaction, something like this, and you want to minimize the probability of user unsatisfaction. So the objective function is the probability that some stochastic function does not exceed a certain threshold. And you can see that all of these approaches can be represented as a special case of the first one, where we are maximizing the expected utility by defining the utility in different ways. So if you define the utility to be minus f, then basically you are minimizing the expected cost. If you define, for example, the utility as an indicator function, whether this stochastic function, let's say user unsatisfaction, whether the user unsatisfaction is less than t or not, then you can formulate this probability term as the expected value of this u, right? One very important part of this is how to model the feasibility. So you have uncertainty in some of the parameters, in the demands or the quality of the resources, etc. Then how do you define the quality of service metrics? Like, what are you trying to achieve for the users or for the network in terms of the constraints? If you have, so let's say a typical deterministic optimization, minimize Cx subject to Ax greater than or equal B, and X is within certain range. Then if A or B or both of them are stochastic, so usually A and B are deterministically known, then how could you do the optimization? How could you define your constraints or your QoS metrics? Do you say, I want Ax greater than or equal B for all values of A and B, irrespective of the realization of B, or irrespective of the realization of A, I want my constraint to be satisfied? So this is the first approach, which says infeasibility is not accepted. And this is very difficult to achieve. Usually you won't have a solution for the problem in this case. The other approach is to satisfy your constraint only with a given probability, with a minimum probability. That you want, whatever this constraint means, Ax greater than or equal B, you want it to be satisfied only with a probability that's at least alpha. And since you are minimizing the cost, usually the optimizer will not exceed alpha by that much, because this will incur higher cost. And this is what's called chance constraint stochastic programming in the area of stochastic programming. And you can categorize it into two ways: joint chance constraint programming or individual chance constraint programming, depending on your constraints and how do you formulate them. So if you have the deterministic one, you have Ax greater than or equal B. So B is a vector. Let's say is a vector of dimension m. Each element corresponds to a user. You have m users, you want to meet their demands. So if you say, I want the demands of all users to be satisfied jointly with the probability to be at least alpha, then this is joint chance constraint programming. But if each user has its own QoS metric, so I want user I to be satisfied, its rate demand to be satisfied with a minimum probability of alpha I, and I is different, so that you are not trying to meet them jointly, then this is the individual chance constraint programming. And there is a huge research on how could you solve this type of problem. Although it seems just a slight modification to the deterministic one, it's not that easy to solve, because Cplex or any other optimization will not solve this probability thing, right? You want to convert it to another form. You want to find a deterministic way of representing this problem. And this depends on where is the uncertainty. Is it only in the right-hand side of the constraint? Is it on the left-hand side of the constraint? Is it in both sides? What do you know about B, the distribution of B, A, etc.? So we said the first approach in feasibility is not accepted. The second approach is chance constraint programming. The third approach is a simple recourse. So you can see in chance constraint programming, you are not considering for the scenarios where you are not satisfying the constraint, you are not considering how much you are violating the constraint. So you just want to satisfy it with probability alpha. For alpha percentage of the scenarios, you want this to be satisfied. But for this 1 minus alpha percentage of the scenarios where your objective or your constraint is not satisfied, you don't know by how much it's not satisfied. Is it close to B, or is it just getting nothing, or it's close to its demand, etc. And you have a constraint, which makes the problem, depending on the demands and the resources, you might not have a solution, and depending on this alpha probability that you are trying to achieve. Instead of that, you remove the constraint. You say, I don't have a constraint. I include it in the objective function. So there is no constraint about the level of user satisfaction, but try always to satisfy the users. So whenever you don't satisfy them, whenever ax minus b is less than 0, or b minus ax is greater than 0, you incur a certain cost in the objective function. So you try always to satisfy this constraint and not to violate it. And this is called simple recourse approach. Is it clear? The fourth approach for modeling the feasibility is the two-stage stochastic optimization, and in general it can be extended to multi-stage. It's not necessarily only two-stage. Two-stage stochastic programming with recourse. So you divide your problem into two stages, and this is just conceptually. At the end, you are solving one problem. You're not solving problem one, you get the solution, you solve problem two. It's just one single problem, but conceptually you divide it into two stages. There is something you want to decide about without knowing the particular realization of these stochastic variables. You know the distribution, you know what could be the values of these stochastic parameters, but you don't know which particular realization has occurred. And instead you want to make a decision before knowing that. And then once you have a particular realization of these stochastic variables, you can correct your initial decision, or you can make another decision. So you either make a resource allocation decision in the first stage before knowing the particular scenario, and then you can correct it under each scenario. Or we used it actually to model joint network deployment and resource allocation problem. So I want to deploy the access points or whatever resources you want to deploy, and this is static, I cannot change it. So I want to make this decision as a first stage decision without knowing the particular realization of the stochastic variable, and then I can tell how to do the resource allocation under each scenario. But this whole thing is just single problem that you run it once and you know both the optimal values for both decisions, the first stage and the second stage decision.
Is there any relationship between Q and alpha?
Is there any? Yes, you can formulate it this way. So the variables, this is not equivalent transformation. Like it doesn't give you the same level of user satisfaction, but you can design your queue, of course, depending on how much you want to satisfy your users. You tell how much cost the objective function will incur to prevent this from happening. So queue prevents a trade-off between your user satisfaction and your cost. If you don't really care much about the cost, you want to satisfy the users almost always, as long as you have enough resources, then you can set the queue to be very, very high. And then this CX is almost not considered in the optimization. And if you set the queue to be very low, then it only cares mainly about the resources and just does not care much about satisfying the users. So yes, the queue is related to the level that you want of user satisfaction, which is alpha there.
Very high or very low, do you mean relative to the B minus AX, or is it just some random?
What's that?
By very, you can set very high or very low.
Depending on what is the range of this expected term and what is the range of CX, of course. So if CX is just integer values and this is something in the range of 10 to the power something, yeah, you want to set the queue such that this second term dominates the first one, or you set it such that the whole thing is negligible to the first term.
Is there any analytical way of arriving at some queue, or is it by trial and error?
No, you know what is the distribution of P, what is the distribution of A. Then you can tell what is the expected value of this term.
Yes.
Then if you say, let's say this value has a range between 10 to the power 3 to 10 to the power 4. Then if you set your Q even to 1, and given that C is just 1 and X is just integer 1, 2, 3, 4. So if you set your Q to 1, this would be enough to make this dominating the other one, right? Because this one anyway is 10 to the power 3, 10 to the power 4. Setting a Q to 1 makes this dominating the first one. Or if you want the other way around, you want to care about the cost, then you set it to 10 to the power minus 4 or something, then you make sure that's always less than 1. Then you don't care about it. Not much. So this is what we mean by two-stage stochastic optimization. So you have the first stage decision X, which does not depend on the particular realization of the stochastic variable. And then you have this second stage pair scenario. So for each scenario, you are trying to optimize something else. But this second stage is included in the first stage in the objective function. So the objective function of the whole problem is Cx plus the expected value of the second stage objective function. So you don't solve problem 1 and then you get x and then you go and solve problem 2. It's just conceptually that's what it means. But at the end, you can formulate this whole thing as a single problem. You solve it once. We'll have one example to explain how, what does that mean exactly. Oh, this is the example. So one example is not related to wireless here. It's capacity expansion planning. So if you have a set of electric generators I, a set of demand sites J, and then you know what is the total generation capacity that can be installed at each, can be installed in total. The unit cost of installing capacity at generator I, the unit cost of sending energy from generator I to demand site J, and the unit subcontracting cost for demand site J. So you have total generation capacity. You have for each generator what is the cost of installing a unit capacity. So if you are talking about here solar panels, so the cost for each unit cost for installing capacity at each generator, and the energy transfer cost, and also the subcontracting cost for demand side J. And you have two stochastic data here. You don't know what is the available fraction of capacity allocated to generator I. If we are talking about solar panels, etc., you don't know how much energy at a given time you have, or it's available at each generator. And also the demands at each site are stochastic. So these are the two stochastic variables. And you want to decide about where to install how much capacity to install in each generator. And this is the first stage decision that you want to make before knowing the realization of these two variables, the demand and the available fraction of the capacity. And then for each scenario, you want to decide how much energy to move from generator I to demand side J for all I and J. And in case it's not enough, you want to decide how much energy to subcontract for demand side J. Is the problem clear? Then this is how we formulate this problem. Where to start? So in the first stage, you are trying to minimize the cost, subject to you cannot install more than B. So this is the total generation capacity that you have. And under each scenario, you are trying to minimize also the cost for the subcontracting, the cost for transferring the energy, while satisfying the demands.
When we talk about domain here, I'm assuming K and X are all, they're both real numbers?
K is constant, X is this decision variable. So Xi
Is binary.
is not binary because we said it is the capacity installed to generator I. It's like per unit, how many unit capacities. So it's integer.
Okay.
And could be in general just linear, not necessarily integer. And Ki is the cost, unit cost of installing capacity at generator I. So then the first objective function, the first part of it is basically the cost of installing the capacity. How much capacity you want to install times the unit cost per capacity. And then you have the constraint in the total generation capacity that you can install, which is B. So B is the total generation capacity that can be installed. The second stage, also you want to minimize the cost. So you want to satisfy the user demand. This is the constraint for satisfying the demands for each demand side J. But you want to minimize, you want to satisfy it with the minimum cost. And the cost here, they have two parts. The transfer cost from whatever capacity you have installed at each site, at each generator I, plus the subcontracting cost. Without exceeding, so the sum of Yijn does not exceed the available generation capacity. So you installed how many solar panels, but you don't know how much they are going to give you, right? The uncertainty is in the availability of each solar energy in each of these panels. And Y and J are also non-negative. Is the optimization problem clear? We'll talk about one approach in solving it using deterministic equivalent program. How do you combine these two problems? At the end, I have a problem that I can feed it to Cblix. Later, we'll talk about this. But is the problem currently clear? And this is kind of comparison between the different approaches in feasibility, not accepted, chance constraint, simple recourse, and adaptive multi-stage optimization. And we have already talked about this. So in feasibility, not accepted is not something that you can do in many cases. The chance constraint, stochastic programming, it's one common approach, but it does not say anything about what happens for the unsatisfied scenarios. You are only caring about the probability that I want to satisfy alpha fraction of the scenarios, but doesn't say anything what happens for the 1 minus alpha. The simple recourse, it cares about the magnitude of violating the constraint and not only the probability. And it makes the problem simpler because there is no constraint. You're just trying to do the best that you can, and you can control setting the queue. But there is no adaptability. There is no, although it's called simple recourse, but there is no really that recourse action compared to the adaptive or the multi-state case. Solution approaches. One approach for solving stochastic programming is to find the way to derive its deterministic equivalent program. Exactly. Given what you know about these stochastic variables. And this is not necessarily depending on your problem, it might not be that efficient approach to do, because it might end up having a deterministic problem, but that is very complex to solve. So how do we convert a general chance constraint stochastic program into deterministic program? We want to replace this probabilistic constraint, and we want to remove these stochastic variables. If you know the distribution or the set of scenarios that A and B may take, then you can basically, you want to count for a given allocation, you want to count how many scenarios are satisfied under how many scenarios AX is greater than B, and you sum the probability of these scenarios. You want it to be greater than alpha, right? That's what the constraint means. I want the probability of satisfying the constraint to be at least alpha. So if under a given decision variable X, you can evaluate whether this constraint is satisfied under each scenario or not. And then you want the sum of the probabilities of the scenarios under which this is satisfied to be at least alpha. And that's what we are doing here. We are introducing a new binary variable for each scenario. So if AX under scenario omega, for given solution X, if AX is greater than B, then U would be 0, right? And then you are summing the probabilities of the scenarios under which this constraint is not satisfied. U is 1, and you want them to be less than or equal to 1 minus alpha. Is this clear? The other approach is if A is not stochastic, it's only the uncertainty in the right-hand side of the constraint, then you can reformulate it using the CDF of B, right? So if you have if B is a stochastic variable and you want the probability that the summation of AJ, HJ is less than or equal B to be greater than or equal alpha, right? But what is the probability that B is greater than or equal this term? It's 1 minus the CDF of B evaluated at this summation. I want it to be greater than or equal 1 minus alpha. So if you know the distribution of B, then you can easily convert this problem into a deterministic problem from the CDF, knowing the CDF of B. Other approximation ways, sometimes it's not easy to solve the exact reformulation of the chance constraint stochastic programming, because the number of scenarios is very high, so you cannot just enumerate all the scenarios and solve this problem. So there are some ways to approximate the chance constraint in a deterministic way using some of the inequalities, Markov inequality, Chebyshev inequality, etc. For some of the cases that we have studied, it doesn't really give you that much comparable performance to solving the optimal problem. So you might start by approximating it using these inequalities, but then you want to do something more than this to make your solution as close to the optimal. And another approach is also the sample average approximation. So you can convert your problem into a deterministic program using all the scenarios, but then find a way to sample these scenarios and not to consider all the scenarios. Sample the scenarios while ensuring that your performance is within like epsilon from the optimal if you consider all the scenarios. So finding the minimum subset of scenarios that you can take without degrading the performance below a certain percentage of the optimal performance. So we talked about the deterministic equivalent program for the chance constraint stochastic programming. For the two-stage stochastic programming, it's the same thing. So the main problem on minimizing Cx plus the expected value of the second stage objective function. So how do we find this expected value? It's just the sum of P of omega for each scenario times the second stage objective function. In this case, it's Q times U. And then you have the first stage constraints, and then you have the second stage constraint for each scenario. So it's a single problem where you can have only single value for x. So you want to decide about it without knowing particular scenario, but you can change your decision of y depending on the scenario that's happening. You can solve this problem as here it's just linear program. Could be mixed integer linear program in Cplex or other type of softwares. But also you could design one, there is one common, one well-known algorithm for solving this two-stage problem is the L-shaped method. And basically you solve for the first stage, you fix the solution, and then you can solve this sub-problem for each scenario and then refine your first stage, etc. So there are some algorithms for solving the two-stage problem other than just solving the full problem as a linear program or mixed integer linear program.
Solving each individual problem, like time complexity too high.
No, then you can do parallel programming. So here you are considering all the scenarios as a single problem. If you can decompose it and solve just the problem per scenario, you don't need to solve all this jointly. You want to solve all this each sub-problem alone, and then you use these solutions to conclude what is the solution of the optimal of the whole problem, like basically the X. It's similar than considering if you have, let's say, 100,000 scenarios. Instead of considering a problem that you consider all of these things in a single problem and you want to solve it jointly, it would be easier to decompose it. And this is the L-shaped method is basically the primal decomposition approach. And there is also the dual decomposition. If you consider this problem, can you decompose it now into separate problems? Are we just putting separate problems together and we are solving them? Or there is some constraint that couples these sub-problems together? The only constraints that couples these problems together is the things that relate to X. That makes it not decomposable. And the dual decomposition is to relax this constraint. So in order to decompose them, you can define X per scenario, X1, X2, X3, and then you say all of them are equal, right? If you relax this constraint, that X of 1 is equal to X of 2, that X is not scenario dependent. If you relax it and you make it scenario dependent, then you can decompose your problem into solve problems with the number of scenarios. And then after solving that, you can use the Lagrange multipliers to relax this constraint on solving the decomposed problems. And also you can use sample average approximation to solve the two-stage problem similar to the single stage, the chance constraint. Is there any questions so far? questions? Okay. So now I will talk briefly about some of the resource allocation problems that we have considered under uncertainty. This is some of the problems. So we talked about joint channel and base station allocation in opportunistic LTE network. Okay, I think let me go to each of these. I will not go into the formulation, just describing the different problems that we have studied. So one problem was about joint channel and base station allocation in opportunistic LTE network. There are two main things in this problem. The first thing is about full duplex. So if we have a full duplex small cell where the user equipment or the small cell can communicate with the user equipment and the base station simultaneously in the uplink and the downlink. So the small cell can receive data from the base station while sending to the user equipment, and also it can receive data from the user equipment while sending to the base station, and this results in doubling the spectrum efficiency of the small cell if you have complete self-interference cancellation. This is one thing that we wanted to investigate, and different small cells in the network could have different self-interference cancellation capabilities and then different spectrum efficiencies. And then I have a set of channels in the network that I'm operating over these channels in a secondary manner, only as a secondary user, and the availability of these channels are only stochastically known to the secondary users. And I want to do channel and base station allocation to the users subject to some probabilistic rate demand constraints that I want to be satisfied. And the uncertainty here is only in the availability of various channels to the secondary users. This is one problem that we have studied, and there is a paper. It's the first reference. It's published in 2015, and we formulated chance constraint stochastic programming as well as two-stage stochastic programming approaches. So we talked about static allocation as well as adaptive allocation, where you have the ability to correct your channel assignment after the uncertainty is exposed. Another problem is in LTE Wi-Fi coexistence. So some of the coexistence approaches are based on dividing the time between the LTE and the Wi-Fi. Using this adaptive on-off cycle, or using the concept of ABS allocation. So the LTE will be silent during some of the ABSs, almost like subframes, so that the Wi-Fi can use the spectrum. If from the LTE perspective, if it doesn't know the exact availability or activity of the Wi-Fi over different channels, and if you want to do some sort of proactive channel allocation for the LTE users with some probabilistic guarantees, without knowing what would be the availability or what would be the number of almost blank subframes that comes out of the sensing in each frame for the LTE users. So the LTE, in one of the approaches, the LTE will sense in each frame, and based on the detected Wi-Fi activity, will decide how many almost blank subframes to leave for the Wi-Fi. This changes from one frame to another. If you want to do some proactive channel allocation for the LTE users without knowing the exact activity of the Wi-Fi user ahead of time, you know some distribution on the number of ABSs that you might allocate, or the distribution of the Wi-Fi activity, then how could you also do this type of resource allocation? Recently also, this is something under submission, we talked about the CBP controller replacement problem in software-defined wireless networks. So very recently, there are some few architectures that assume or propose to have a wireless link between the SDN controllers and some of the controlled elements in the network. This wireless link, as in any other types of wireless network, you will have many types of uncertainty. The controller replacement problem has been studied extensively, but only for the deterministic case and for wired connections. So if you have a wireless connection and you want to satisfy some delay constraints for these controlled elements, so the response time to the controlled element wants to be less than something like delta with a given probability. You want to meet the delay constraints or the response time constraints with a given probability, how do you formulate this problem? Considering the uncertainty, the channel, so the flow setup request from the element to the SDN controller might not be delivered successfully, so you want to retransmit. The number of retransmission is stochastic following geometric distribution. Also, if all the controlled elements that are assigned to a given controller are sharing the same channel in CSMA fashion or in TDMA fashion, you have also uncertainty in the delay, in the channel access delay. So you have different sources of uncertainty, and you want still to provide some guarantees about the response time or the delay to these controlled elements. We also considered software-defined cellular networks. If you have, and this concept is already there, applying the SDN to the cellular networks. The same thing, we're talking about control replacement problem. What are the optimal and the minimum number of SDN controllers that you need to place in the network, and what are the optimal locations of them to satisfy some delay constraints for the communication between the SDN controller and the eNode Bs under the uncertainties of the request rate or the load on each eNode B, from each eNode B to the SDN controller, which comes from the uncertainty of the user distribution. So the users in the cellular network are mobile, and then the number of users per cell or the request rate, the aggregate request rate from each filling station to the SDN controller is stochastic. Given this uncertainty in the request rate, how could you determine what is the minimum number of controllers and their optimal locations and the optimal assignment of the controllers to the base stations subject to some delay constraints? And the last thing, we have some work under submission about also millimeter wave networks. And in addition to the other types of uncertainty that typical wireless network have, because of the highly directional links in millimeter wave link, also the uncertainty in the user orientation, and the uncertainty in the uncertainty in the user orientation. If the user just moves its equipment a little bit, then the link might be no longer available. And also the beam width of the user equipment will vary depending on whether he has this equipment in his hand or in his pocket, etc. Given this uncertainty or this variations, that very high dynamics that happens, how could you also do deployment, where to place the millimeter wave access points, and also resource allocation, how to assign the access points to the users optimally. So you will end up assigning multiple access points at the same time to a given user in order to ensure some probability of coverage, that within 95%, this user always has a high data rate link. So the solution will be at the end assigning multiple access points to the same user at a given time. So the conclusions, as we mentioned, many types of emerging wireless networks tend to operate in part over a dynamic and uncertain set of resources. There are many examples for that, and this makes their performance susceptible to severe degradation if you design the network only based on the deterministic case, based on the expected value only, or something like this. In addition to the resources being uncertain, the demands could be uncertain. One example is virtualized wireless access networks. I haven't talked about this, but we also have used the stochastic resource allocation in virtualized wireless access networks. Managing resources in such stochastic networks while ensuring a certain level of QoS is not straightforward. We suggest to use, or we have been using, stochastic optimization as a powerful tool to handle such resource allocation problems. I talked about the different ways of modeling uncertainty, feasibility, and optimality, and the different optimization approaches, the static and adaptive approach, including chance constraints, simple recourse, and two-stage as well as multi-stage stochastic optimization. One important thing is developing approximations to various stochastic programming approaches or problems is very active research area. So stochastic programming is a very powerful tool, but also the complexity is a big issue there. There are lots of research on this in the operational research area, but there is still also ongoing research on solving or approximating different chance constraint programming problems or multi-stage stochastic programming problems. And that's all from my side.